Gracias.
Gracias a usted por haberme invitado.
Okay, so we move on to the next speaker in this section flash for this symposium. Our next speaker is Dr. Jaclyn Brusso. Are you there, Jaclyn? Oh, yeah, I can see you now. So she's full professor and vice dean of equity, diversity, inclusion, and professional development. Dr. Brusso's research focuses on understanding and ultimately controlling the self-assembly
Sorry, I think we lost Alejandro. Can you hear me well, Jaclyn?
Yes, I can hear you.
Okay, then I will take over. Maybe let's wait for a few seconds.
Okay.
Whether Alejandro recovers connection. It looks like.
Can you see my screen okay and hear me okay? Okay, perfect.
Yes. We can see you fine. Sorry about that. So Alejandro says it's a low broadband connection, whatever. So I will take over then, and I will keep with your introduction. So as Alejandro was saying, Jaclyn is full professor and vice dean of equity, diversity, inclusion, and professional development at Ottawa University, right? Dr. Brusso's research focuses on understanding and ultimately controlling the self-assembly of complex p-conjugated molecular architectures with tailored functionalities. Two main areas of research are design and synthesis of liquid crystalline radicals, so LCR, and development of conjugated macromolecules. So she has a lot of publications as first author, a lot of citations, and a very high H index. So we are looking forward to hearing you, Jaclyn. So please go ahead.
Thank you. So thank you very much for that the kind introduction and the opportunity to present here today. It's unfortunate that we all can't be in the same room together, but hopefully we'll be able to do that sometime soon. Today I will be presenting something, I guess, a little bit of a different flavor from some of the other presentations that we've seen so far in this conference, with a focus on exploring the synthesis and the synthetic methodology required to control coordination using imidoyl amidine ligand frameworks. And so through that synthetic control, we can tailor the coordination environment and the nuclearity in the pursuit of building extended coordination networks. Now, when I talk about imidoyl amidines, they're not a very common ligand that's used, which is perhaps surprising when you look at the framework. So shown here on the right-hand side of the screen is the imidoyl amidine, and looking at it and comparing it with the isoelectronic series of NAC-NAC and ACAC, it seems like, and ACAC and NAC-NAC being quite ubiquitous in coordination chemistry, it seems surprising that these imidoyl amidines have not yet been explored. And when we first started to looking into this chemistry, we did a literature search and found that in fact there were very few reports. And so this is about a year-old search, but there were only 174 records on reports that include this imidoyl amidine framework, and that's for all chemistry, and that include the majority of those were in organic chemistry in the pursuit of pharmaceuticals. With only a handful, or I guess two handful of those publications related to the use of imidoyl amidines in coordination chemistry. And so we thought that we consider this very untapped area of research, because not only do you have accessible the NAC-NAC coordination site, but depending on the substituents that are placed at the carbon atoms, we can incorporate a secondary coordination environment. And so what this requires is the development of imidoyl amidine frameworks that are suitable for use as building blocks in the development of these extended structures. And so in particular, what I'll focus on today and what we've been focusing on in my group is the use of heteroaromatic substituents attached to that framework that facilitate a terpene-like coordination environment in addition to that NAC-NAC binding site. Now, we aren't the first ones to explore imidoyl amidines, as I mentioned. I mean, while it's only a few handful of these records, they did come before we started exploring imidoyl amidines. And the first report was in 1996, in which this bismethoxy imidoyl amidine ligand was generated in situ through the reaction of the dicyanoamidate with a copper salt in a methanol solution. And so then, inspired by this work, a few years later, in 2003, Kitagawa isolated the first bis-pyrazyl imidoyl amidine ligand in this trinuclear copper complex, using the same synthetic methodology, just including pyrazyl in the reaction mixture. And then this can be further treated with EDTA to isolate the mononuclear copper complex, which then leaves that terpene site open and available for secondary coordination with another metal salt. And so they generated a series of mixed metal trinuclear complexes. The first example of the imidoyl amidine, the bis-pyrazyl imidoyl amidine ligand being isolated as a free ligand was achieved by the treatment of this trinuclear copper complex with ammonium sulfide. And then with the free ligand in hand, this could be then treated with other metals. In this particular example, or this publication, the authors used nickel to generate a mononuclear nickel complex and a trinuclear nickel system. In addition to the bis-pyrazyl derivative, there have been reports of bis-pyridyl imidoyl amidines. So the first was in 2002, and that ligand framework was generated through the thermal decomposition of triazine, in which the authors report, or I guess postulate that what's isolated is an insoluble, uncharacterizable powder that upon treatment with EDTA, they can isolate this mononuclear copper complex. The bis-pyridyl imidoyl amidine has also been isolated or has been reported as a ligand in a palladium complex. In this particular case, the ligand framework was fabricated through the in situ reaction between a nitrile and an oxime. And then a few years later, kind of combining these two ideas by generating this amidoxime starting material and reacting it with manganese, a manganese analog, a manganese complex coordinated to 3 of these imidoyl amidine ligands was reported. And then the final example that I'd like to share is this dinuclear copper complex that the copper ligands are bridged through this bispyrimidal imidoyl amidine, which is fabricated through thermal decomposition of the triazine, similar to that first example reported in 2002 for the bispyridyl ligand framework. And so once we start looking at what was in literature, it became a little bit more clear why imidoyl amidines hadn't been studied to much of an extent. And that's the one similarity that all of these reports have is the fact that the ligand framework is generated in situ. And so that limits the control of the reaction conditions and the metal salts that can be used. And so we looked at this as an opportunity to, if we can isolate the ligand framework, then we could really explore its potential as a ligand in coordination chemistry. And so to that end, we found that we could take pyridyl or pyrimidal nitrile, react it with ammonia gas, and isolate the imidoyl amidine in very high yields. We could do 10, 20 gram reactions and really high purity. And so these ligands can exist in either the diamino or the amino-imino tautomeric form. In the case of the pyridyl derivative, it exists as a single tautomer in solution in the solid state. In the case of the pyrimidal imidoyl amidine, it exists as a mixture in solution and as the diamino tautomer in the solid state. And so now that we had this ligand in hand, we could start exploring its coordination chemistry. The first step was to take first row transition metal salts and do benchtop reactions. And we found with a variety of metal salts under atmospheric conditions in either neutral or basic conditions, we could isolate these coordination complexes in which the metal ion is coordinated in a bidentate fashion to 3 anionic ligands. Here's just an overlay of the 3 derivatives, just highlighting the similarities between them. We were able to confirm the oxidation state of the central metal ion through magnetic studies, which indicate that when coordinated in bidentate fashion to 3 ligands, we have low spin metal 3 complexes. And so once we had this, and I do mention about basic and neutral conditions. Under neutral conditions, the reaction is a bit slower, so you can get bigger crystal growth, whereas under basic conditions, the yields tend to be higher. But either way, they generate the same compound. And so then we wanted to access coordination in the terpene-like pocket. And so here, we looked to running the reactions under acidic conditions, as that leads to protonation of the imine nitrogen atoms that blocks then the coordination in that site and facilitates coordination to the terpene-like pocket. And so under acidic conditions, and again, we use some first row transition metals, and the oxidation state and coordination environment about the metal center stems from the metal salt that's used initially in the reaction. And so under acidic conditions, we have these neutral ligands with tridentate coordination based on the magnetic analysis. When we have metals coordinated in the tridentate site, they are high spin metal ions. And we also have this acidic proton that we thought would be beneficial that we could deprotonate to facilitate the development of extended systems. And so to coordinate a secondary metal or extend into a coordination polymer or network. Unfortunately, we found that upon treatment of this mononuclear complex under basic conditions, it converts into coordination and with the metal ion in a bidentate fashion. And so we had to rethink how we were going to make these polynuclear complexes, given that these synthons had some limited solubility on their own part. And then what we ended up finding is by switching to use of pyridinium metal salts, we could access different solvent conditions so that we could generate a series of tetranuclear coordination complexes in which we have a metal ion coordinated to 3 ligands in a bidentate fashion, and then 3 other metal ions coordinated in the terpene-like pocket. And so just to highlight the similarities between the mononuclear complexes and kind of that moiety within the polynuclear system, we see this overlay, which is fairly superimposable. And we can do the same thing for the central metal ion. In this case, there is some deviation at the periphery of the molecule, but if you look at the coordination of that central metal between the two systems, they're quite similar. And so based on this, we could come up with so this cartoon representation of the spin states, and in all of these derivatives, we have the iron, the manganese, and the cobalt. We have a low spin metal ion at the center and high spin metal ions at the periphery. And so in kind of keeping with this theme of extending extending the network, we wanted to access square planar core so that we could get a planar molecule and then tap into the axial position to extend the network. And we found we could achieve this by reacting under an inert environment with cobalt, and also we could generate the nickel and copper systems as well. In order to tap into the coordination at the periphery and the tridentate and bidentate site. We turned again to our pyridinium salts, in which case we were able to generate this trinuclear cobalt complex. Again, we can look at overlays with the mononuclear systems to see the similarities at the core as well as at the periphery of the molecule. And so by using our mononuclear systems as a kind of a template, we can come up with a spin state. So in the case of our trinuclear systems, here again, we have a low spin metal ion at the center and high spin metal ion at the periphery. What's particularly interesting or attractive, I guess, about this cobalt trinuclear system is due to the planarity. The molecules kind of alternate in the stack, and that leads to this really short cobalt-cobalt contact between molecules. And if we look at a top view or a bird's eye view of this stack, we end up with kind of this column of our cobalt complexes. And then kind of looking even further at how these columns stack together, we get this kind of columnar network that is reminiscent of discotic liquid crystalline materials. And so just kind of showing that view a little bit differently, here we have these porous channels within the framework, within the I guess, supramolecular structure of these trinuclear complexes. And something that we found that was pretty interesting, well, actually somewhat surprising and concerning at first, but interesting in the long run, when we tried to remake this compound to do full characterization, we found we isolated this, we found a hexanuclear system, which is almost like a dimer of these trinuclear complexes. And so it was very concerning at first because everything was done the same, until we kind of looked at the conditions of our solvent and how dry our methanol actually was. And we found by adding a specific amount of water to our solvent, we can selectively isolate the trinuclear complex, and having very freshly distilled dry methanol, we can isolate the hexanuclear system. And at first look, the hexanuclear system does not appear to maintain kind of that porosity that in the structure, but in fact it does. It's just now we have kind of this zigzag array of these channels within the structure. And I'll come back to this in a minute. And so with this system, we had our ligand framework, and we were really interested in looking at mixed metal systems, given the fact that we could control the conditions to generate mononuclear systems with coordination octahedrally in the bidentate and square planar, as well as have our metals situated in the terpy-like pocket. And then taking advantage of pyridinium salts, we could access polynuclear homometallic systems in which we had our trinuclear, tetranuclear, and then also the hexanuclear material that I just showed. And so the next question, or the next step, would be, can we make mixed metal systems taking advantage of our mononuclear complexes as synthons? Now, as I mentioned previously, with the polynuclear homometallic systems, we couldn't use our starting, it was challenging to use our mononuclear systems as starting materials because they did have specific and limited solubilities. And so in looking towards making mixed metal systems, we really needed to consider the solvent conditions and take advantage again of those pyridinium salts. But in this case, upon isolation, upon generation of our first kind of coordinated core, we could then add a secondary metal to isolate, in this particular case, a trinuclear mixed metal iron cobalt system, or under atmospheric conditions, we could generate the tetranuclear mixed metal system with cobalt at the core and iron at the periphery. So again, by controlling the reaction conditions and the order and method of addition of our metal ions, we could selectively get these mixed metal systems. And so we also sought to explore our trinuclear versus hexanuclear complexes, that whole idea of the wet solvent versus dry solvent, and found that that same principle applies when we have multiple or different metals in the specific sites. And so in this particular example, we have manganese, high spin manganese at the periphery, and copper at the core. So I mentioned previously that I'll come back to this idea of the porosity. So here we have our copper manganese trinuclear complex. It forms that similar kind of columnar like array as the cobalt analog with these I guess these columns or void space within the structure. And what we found with this system, looking at the structure, that these porous channels were formed by a combination of hydrogen bonding, nitrogen copper contacts, intermolecular contacts, and pi-pi interactions within those stacks. And when we what am I trying to say? So what we wanted to see was if these columns were maintained when we activated the material, and to what level was there any was the structural integrity maintained, and if there was any selective gas absorption. And so here we have a plot of not only was the structure maintained upon activation, but we do have a selectivity a preference for high carbon dioxide uptake. And so this is somewhat rare, but has been seen before, and likely due to the higher CO2 absorption over nitrogen, may be attributed to the high nitrogen content within our ligand framework. And I realize actually that I'm running out of time, so I'll go very quickly through my summary here. I hope over the past 20 minutes I've convinced you that imidoyl amidines are versatile ligands, and we've only just begun to really explore their potential. We can isolate mononuclear systems, polynuclear, homometallic, and also mixed metal systems. And so now extending that further, we are looking at the conditions that we can form these extended networks and take advantage of all the coordination environments within the metal sites. And so with that, I was going to highlight some of the other features that we have within these complexes, which isn't really related to porous materials, but I will kind of skip over that a little bit, just to keep within the timeline of my presentation.
I mean, Jaclyn, if you want to extend for, like, let's say 5 more minutes, it's completely fine. So don't worry.
Okay. So I guess some of these the molecular materials, there is based on theoretical calculations, there's an theoretical calculations suggest that we should be able to tap into multi-step spin crossover with our imidoyl amidine ligand framework. And so this is just kind of one example that was used for the theoretical calculations with a variety of metal 2+ salts at the core. And so this is an area of further exploration that we are aiming to use through an external stimuli. As well, we have seen some degree of luminescence depending on the metal, and so this taps into coordinating with lanthanides. And what opportunity we have with the imidoyl amidines is that we can tailor the aromatic group to act as a chromophore to enhance the luminescent properties of these metal ions. As well, we are exploring through collaboration some photocatalysis with some of our mononuclear complexes, and as well looking at MRI contrasts with our multi-centered mixed metal complexes. And not only have they shown enhanced MRI contrast compared to gadolinium standard, they also are redox. The contrast is related to the redox environment, and so we can have target-specific imaging. And so the next step with this would be then taking it from target-specific imaging to personalized diagnostics. And so with that, I would like to thank, in particular, Raul. He was a PhD student who graduated a year ago. He really kind of spearheaded this project in the group and did all the preliminary work. And then now Alex has taken over working with this system, and he explored the gas absorption and luminescence, which is done in collaboration with my colleague Murali. And I also need to recognize Rodolphe, who I presented. Well, I didn't actually present the magnetic measurements, but the results of the magnetic measurements that he had run. And of course, I have to acknowledge the funding agencies, and thank you all very much for your attention. Thanks.
Thanks a lot, Jaclyn, and congratulations on a really, really nice presentation. There's a lot of feedback. Maybe I would start with one of my own, because it popped out on my head while you were passing through your slides. When you show, I mean, it's nice enough that you observed some selectivity in absorption of nitrogen and carbon dioxide for your trinuclear complexes. But I was wondering whether for the cobalt or for the bimetallic complexes, have you determined or maybe have an estimation of the surface area of those crystals that you synthesize?
That's an excellent question. So no, we haven't explored the surface area of the crystals this far. The measurements that were done would have been on powdered samples as opposed to well, it would have been microcrystalline samples, so I'm not. It wouldn't have been on large single crystals.
Yeah, are you asking me if? Sorry, I didn't understood.
No. I'm mentioning. So I don't know what the surface area of the. We haven't.
All right.
No.
All right. Yeah, I'm guessing it should be. I mean, if the area is large enough, you can just maybe try it in some absorption equipment, and should be getting some area, maybe not really exciting, but just one number to have an idea of what it looks like. So thanks. There's another question from Germán Gomez. He's congratulating you on your nice talk, and he has two questions. The first one is, do you plan to use this nitrogen synthens for the design of high energy materials? He thinks that the combination with silver will be a good option. What are your ideas about this?
So to make sure I understand the question is, have we looked at using these for high energy materials, and in particular coordinating them with silver?
Yeah.
Okay, so these are actually fairly stable, and I think it's related to there's delocalization of the pi system as well as carbon atoms between the nitrogens, and so they're not that explosive, or they're quite stable, but that is the idea of and coordinating with silver. So for their high energy materials, we are working on that, but we're trying to move away from metal salts and look at all organic systems. And so using energetic organic cations and anions, and yeah.
Okay. And the second question is, do you see these ligands as potential ligands for lanthanide of actinide, uranium, luminescent or magnetic crystalline systems?
Yes. So especially given the fact that we have, so I only presented the pyridyl and pyrimidal derivatives, but we can really put a variety of functional groups attached to the carbon. And so we could really tap into the chromophore aspect by so some examples of thiophene or bithiaphene, so that we can tailor the absorption profile of the complex for the energy transfer.
Right. Yeah, and Herman also points out that maybe its triplet state matches well with lanthanide to improve antenna emission.
Yeah. So we are looking into that. Yes.
Thanks. Yeah. Okay. Okay. Then I think we're now have to move on to our last speaker, and thanking Jaclyn very much.